Good afternoon.
Hello.
Jonathan, did you get my email about the calibration? The calibration needs to be included as well.
Yeah, sorry about all that. I've just I'm used to the procedures, I guess, being considerably more specific, I guess. He'd always like grab a flask, fill it with oil, and these ones aren't as specific, so I'm kind of I have to fill in some blanks, I guess.
Well, they just have to be specific enough at your end that you could do it without the lab manual if you were asked to.
Right.
That should be your guidance.
Okay. I'll do that then.
It shouldn't be more than a page, maybe two, including the results.
Yeah.
Hey guys.
Sorry, hey Francisco.
I got my mirror.
Oh, that's good. Now you can look at yourself.
Scary thought.
Hello.
See, I did you a service, Francisco, you know. I did. Hello, whoever that was. I'm sorry. I didn't see who it was who came in. Might have been Victoria.
That's right.
Might have been. All right.
So we're aiming for the test to be next Wednesday.
More than aiming.
Next Wednesday. Wishful thinking on my part.
Wishful thinking. Well, yeah. So there's no school on Monday, so there won't be a class on Monday. I know it's still Zoom, and you know technically I suppose I could still get on and do a class, but I won't because it's a public holiday, and you know you guys need, you know, I think I'd get in trouble.
You couldn't say you're English and that you don't believe in the American holidays?
I'm not English,
Or what are you?
I'm Australian.
Australian. Yeah.
Australia, mate.
Confuse the Dr. Moore told me you were English. That's right. I didn't confuse it. She told me that you were English.
Who did? Sorry?
Dr. Moore. Gracie Moore.
Oh, well, she's wrong.
Yeah. And
yeah.
Jeez.
Yeah.
I'm from Puerto Rico. You can call me Cuban if you want.
Oh, no, I'll just say you're Puerto Rican.
Sounds good.
Yeah.
I'm going to text Dr. Moore, making me look bad.
No, I don't want any trouble from her either, you know.
Too late, buddy. I'm texting her right now.
You're a cruel man, Francisco, a cruel man. All right, so it's 12:31. Let's get started. Enough of this banter. All right, so we're talking about halogenation reactions, and as I had pointed out last time, the pattern is fairly simplistic. What it involves is reaction of an alkane with Cl2. The Cl, one of the Cl's replaces one of the H's, and the H it replaces joins with the other Cl. And I went through that last time. So the upshot of that is, these are examples of very much like what you would see on the test, about same difficulty. So let's look at how you would handle these kinds of problems. It's actually not as bad as it seems, especially once you get used to things. Yeah, I've got to open my paint here. Okay. Hmm. I'll move you all to the bottom here. All right. So, okay. So looking at this first one here, it's a matter of where the chlorines can go, and we've got to take symmetry into account as well. And the way to do that, I think, is to letter carbons that are the same, have the same, related by symmetry. And the way we do that is we can draw symmetry planes, like this would be a symmetry plane through the middle there. This would be a symmetry plane as well. I haven't drawn that very straight, but yes, has a symmetry plane as well. So if I was to label these, what I can see is I can see a few different carbons. I can see this one, A, B, C, and D. And that's it. Those are the 4 different ones that are on there. All the other ones have the same letters. So it'll be A and B. This will be C over here. That'll be C, B, A, D. You don't have to obviously do this for all of them. It's just the ones that are the same. There we go. So there should be 4 different places we could put a chlorine. Does anybody have any questions about that? I wish that symmetry was something I could teach, but it really isn't. It's something you sort of see or you don't see. And it's a matter of getting to the point where you can see it, I guess.
I have a question.
Yeah.
So how do we know only one chlorine is going to attach to this compound?
Because I'm telling you it is.
Fair enough.
Yeah. Let's just assume it's one. But you're right. I mean, more than one could. But let's just say that only one is attaching, okay? So what would be the products then? So for this one, well, actually, I won't even draw them out. I'll show you them because I have them here on the page, and I don't have to draw them then. Okay. Don't be cruel to me. I knew you would be. All right, there we go. That all are. So the attachment points. This one's for A, this one's for B, this one's for C, and this one's for D, plus HCl. So those are all the possible products. Okay, does anybody have any questions?
I have a question about problem number 2, looking at the answer key.
Well, I was just going to do number 2 now.
Read my mind.
All right.
I do have a question.
Yeah.
I just want to confirm. So we're doing the other reactant is going to be above the arrow, and then is that the solution that the reaction is happening in below the arrow?
No, that's H nu. That's light energy.
Light.
Yeah, that's what causes the initiation step, the Cl2 to break apart into 2 radicals.
And is it specifically energy? Can it be heat?
No, it has to be light.
It has to be light. Okay.
For Cl2, it has to be light. That's what will break it apart. I'm not sure what heat would do. Heat might cause it to do something else, I don't know. But light will cause it to turn into 2 radicals. Excuse me, sorry. All right, does anybody have any questions? All right, let's go back to here. Maybe I can put you all over on the other side here. Will it let me? No, it won't. Okay. All right, so for this next one here, let's put the letters on.
think you can move the black bar where all of us to any part of the screen, the bottom, left, up and down.
Yeah, but it won't let me put you on the left. I mean,
If
I'd
you,
like-
I believe you can just drag like above where your name is. There should be like a black space. Click and drag it
oh, hang on. Oh,
anywhere.
there you go. There you go.
There you go.
Hey, I figured it out with your help. Thank you.
No problem.
All right. Let's see.
Watching you struggle is only funny for so long.
Ha 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 ha. Yes, watching me struggle is just frustrating. All right. So we've got A, and then we've got B, and then we've got C. Now, Sierra, I think you were going to ask me about this one here.
Yes.
Oops. Yeah, it turns out that this actually is related by a plane of symmetry here. There. Which makes those the same. And there is a plane of symmetry down the center here as well. So the answers to that one are just those three. And I think, Sierra, your question was going to be, why don't we have a CL coming off the top here as another answer, right?
Yes.
Yeah, and the answer is because it's the same. Think about flipping this, flip this one over like a pancake, it'd be the same thing, right?
Gotcha. Yeah, I see it now. These are so hard to see. Like I saw the middle symmetry and I was like, oh, it's just like you just flip it over that axis, but I got you now.
Yeah, there's more to it, isn't there?
Yeah, it's
So
a trick of the eye.
Yeah.
That's because either of those methyls could be part of the parent chain.
Yeah, you can. Yeah, but I mean, they are related by symmetry, even if symmetry in that part of the molecule. All right, this one here. Oh. Okay. So all these are actually the same. And you'll notice, interestingly enough, that I didn't label here and here. Oh, do I just have something against those carbons? It's interesting, isn't it? Hmm.
They just used all their bonds, right?
But no, Jonathan, can you be more specific about that comment? You're on the right
Sure.
track.
So those carbons already bonded to 4 other carbons. They don't have any more available bonds, right? And when it's bonded to 4 other carbons, it can't bond to chlorine. I mean, that's logic to me. I'm not sure what I'm missing.
All right. But you got to remember that the pattern is that the Cl is actually taking a hydrogen, replacing a hydrogen. If there ain't no hydrogen there, which is basically what you were saying, Jonathan, but I'm just being a little bit more exact.
You wouldn't mark
about
that
it.
wrong on a test, would you?
Oh, no.
Okay.
You were, But anyway, there's no hydrogen there for the chlorine to replace. So there can't be a chlorine there. And you're right. If you did try and draw a chlorine off it, it'd look silly. It would look strange. So there's only 2 products here, and there they are. And it doesn't matter where the Cl goes, which A it attaches to. Any of those will be fine, but they're all the same. They are all the same. All right. So do we have any questions? Check out number 8. Number 8's cool. See if you can draw that and then label it. Label it A, B, C, and D. Number 8. Kind of looks like a tree, but it's winter time. So how many different kinds of carbon are there on this one?
Just days.
They're all the same. They're all the same. Yeah. So there's only one product. Well, plus HCl.
How do you know they're the same?
Because they're all related by symmetry.
Oh.
Can you draw that?
What do you mean, like the symmetry planes?
Mhm.
Yeah.
Okay, well, I'll tell you what. I'll be a little bit more, I'll draw it a little bit differently. Now, if I draw it like this, it's kind of like a snowflake, isn't it? You got a plane of symmetry through here and through here. And of course, we can't label anything that's already got 4 bonds on it. But if you've got 2 methyls or 3 methyls connected to the same C, they're always going to be related by symmetry. You've got to remember these are 3D structures, right? All right, any questions? All right, so I do have all the answers down here, not labeled though, but you can see where the CLs are and you can see how they would have been labeled. All right. So that was pretty much all I had wanted to cover with that, and then I wanted to go over what the test would look like and make sure you're all okay with that.
Dr. Musgrave, I have a
Yeah.
question.
Yes, Keisha.
So you only use B, C, or D when you have more than one line of symmetry? Is that?
Well, no. You use B, C, and D when you have more than one kind of carbon.
Oh, okay.
I mean, you know, if you got something like number 6, right? If you've got number 6, then this would be a separate carbon. That would be the same. That'd be the same. That'd be the same. That'd be C. That'd be C. And this would be D and D. So that would be an example where you'd use all of those because they're all different, the A, B, C, and D. But then it's a plane of symmetry right through here. Is that okay, Keisha?
Yes.
Okay. All right, so you can look at that.
I have a question, Professor.
Mm-hmm.
In an actual reaction, how are we at all able to predict which one of those different molecules we'd get?
Well, as it turns out, you'd probably get all of them, but in varying amounts. In varying amounts.
Depending on like temperature and pH and things like that.
Actually, more depending upon how many C's are attached to the bond in question. So the most popular one here, for example, would be C.
Mm-hmm.
Because that one is what we call tertiary. It's got 3 carbons connected to that carbon, which means that it would stabilize a radical more at that point. Whereas the one that would be least would be A, because that's on the end, and that one doesn't tend to stabilize radicals as well.
Okay, so we'd get like, I'm just gonna throw out numbers. We get like 60% C, 10% B and D, and whatever else A,
Yeah.
right?
Mm-hmm.
And then if you wanted to, I guess, improve the quality of your reaction, you would reverse the reaction and then redo it over and over again?
I don't know. No,
No?
I think it's just going to be what it's going to be.
Okay. There's
Yeah.
no point in... Okay.
Nah. But anyway, we'll learn more about hyperconjugation when we get to SN1, SN2 reactions. It's a similar concept, what I was just talking about. All right, let's have a look. Okay. So the first one here, it says dipole. That's the same as polarity, and we talked about how to solve those kinds of problems. At the boiling point, you have that's your intermolecular forces, and the solubility, that was intermolecular forces as well. And the HCN bond angle, that was about hybridization. We got the acidity question. We've got the resonance question, along with a pairing to acidity as well. We got the atomic orbital diagrams that I told you about. We've got how to figure out hybridizations. And the isomer problem is going to look like this. Now, it doesn't matter how many isomers there are, it will only ever be 7 points, and you can see that here. And then, drawing all the possible structural isomers you can here. And as I said, it would be less than 15. Functional groups, and we have to circle the functional groups. The naming here, where you've given the structures and you have to name them. And then the formulas, and you have to come up with the structures. And then the last one here. So I'll just go through number 10 because we were just doing it. And then I'll go through the isomers because somebody else had asked me about that last time, so I'll look into that. I think I already did this one, didn't I? I did. Let me get another test here. All right. So for this one here, where are we? Here we go. So for the first one, the answer is just going to be CO2 plus H2O. You don't have to balance it, but whenever we do any hydrocarbon combustion, that's what we're going to get, CO2 and H2O. Think about what you do. You create a lot of CO2 and H2O as well. If you look at all the processes like the Krebs cycle, you look at what it produces a lot of CO2 and a lot of H2O.
So if we add oxygen to any of these hydrocarbons, we're just going to get carbon dioxide and water.
That's right.
Every time.
Every time.
All right.
So for this one, I'm going to label the carbons A, B, B, C, and D. So that'd be 4, and the products would look like this then.
Would we also include HCl? Okay, there we go.
I was getting there.
So is the line of symmetry with this one straight down the middle and they share that the C and D?
Mm-hmm. Yep.
Okay.
Yeah, now sometimes people look at that and they say, well, hang on, why isn't D and A the same? Well, they are methyl groups, yes, CH3s, but the A's are connected to CH2s, whereas the D is connected to a CH. That's enough to make it different. But there is a plane of symmetry down the middle.
Thank you.
All right, does anybody have any questions?
Will there always be one combustion part of like question 10?
Could you repeat that, please, Courtney?
Will there always be like one combustion reaction and then one radical?
Yes.
Okay.
Yes. That's pretty radical, isn't it? A little bit of chemistry humor. All right, does anybody have any questions? about number 10. Number 10. All right, let me do the isomer question here. I'm going to do the isomer question. Isomer. If I can find him. There he is. All right, so draw possible structural isomers. Notice I don't say how many there are, right? I don't say how many there are. No repeats or omissions. Please show line structures only. And then I give you a key here just to remind you how many bonds things have. So there's no excuse for getting the bonds wrong because it's right there. All right. Let's see, what have we got? We got C2H2O F4. I don't want to do that one. I'm not doing it. I refuse to do it. I'm going to go back to the other one because I liked that one more. I'll do this one instead. Okay, C4H10O is the one we're doing. I like this one more. Okay. C4H10O. So the combinations are going to be the ones that involve C and O, so the 4 C's and an O. So let's look at the different ways that we can express that. That's an easy one, putting it off the end. Then we can start moving it along the chain, so that would be fine as well. Then we can start putting it in the middle of the chain. So that would be fine as well. Then we can start branching things. That would work. Let me think. Other places I can put things. Any other thoughts? Any
If
other
you put
branching
the
a carbon off of another carbon.
Can
Like,
you give me,
sure. So if you do the CCCO, and then you have a C attached to one of the middle C's.
oh yeah. There we go. So do that and then that, right? Or that and then that. Now somebody else was trying to talk at the same time.
I was just wondering if you put the, like, where your pointer is, like, if you put O, C, C, and then, like, the 2 C's branching off of the NC, is that the same structure?
Let me see if I can do what you're asking here. So, can you say it again, please?
So oxygen attached to a carbon, attached to another carbon, with the 2 C's on the end.
Like this?
Yeah,
That would be this one.
that's the same.
Yeah.
Oh, yeah.
Isn't the second one on the left side and the one on the bottom right the same?
Bottom right, left side. Which one? I'm sorry.
The second one on the left side?
This one? This one here?
Yeah, and then the one on the bottom
And
right.
this one?
Yeah, are they the same?
Yeah, they're the same. They are the same. Thank you. I was just testing you to make sure that you're understanding.
Yeah.
All right. Are there any others that anybody can think of, or any that you might think are doubles?
Could you have a square of carbons with an oxygen on it?
No. And the reason is a square will end up losing 2 hydrogens. Because if you count up the number of hydrogens you can have on that, it can only be 8. And we're specifically looking at C4H10O. So anything with double bonds or circles will be out.
Well, then what if you replaced one of the carbons with an oxygen in the square and then had a carbon off the end? That would make 2 more hydrogens open, right?
Well, not enough. No, let me show you. Let me show you. So you do this, right, and do that. So then you got 3, 1 is 4, and 2 is 6, and 2 is 8.
Still too short.
Yep, still too short. So no circles. No circles. No double bonds either. All right, any other questions? Okay. So now we can do our line structures. 1, 2, 3, 4. That would be OH. So there's no F's or anything to worry about here. And all right, so that would be all of them there, I think. So 1, 2, 3, 4, 5, 6. I think there's 6.
I have a question.
Yeah.
Can you explain the 4-carbon chain with the oxygen on the third carbon? It's this line structure.
What, this one here?
Yes.
Okay, so that's 1, 2, 3 carbons, and then the O, and then a line to this C here. Remember, each point represents a C. So there's a C here, 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 and here.
Okay.
Likewise, on the one below it, C, 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 and C. There's always a bond from the C to whatever.
How come there's not a like you didn't take a line down for the oxygen on the line structure and you just added it to it?
I'm not sure exactly what you're asking.
Like, I guess branched it?
Branched it. Can you tell me which one you're asking about?
The CCC and then the O on the third carbon.
No, this one here.
Nope, the one above it.
The one above it, this one.
Yes.
So yeah, so well, I did 4.
Oh, you know what? I was actually looking at the one below it. I'm sorry.
Okay.
Sorry. Got it.
Yeah, sorry, I was using my room here. All right. Okay, any other questions? All right, any questions at all about the test at all?
Yeah, I have one.
Yes, Nora.
Can you do one where you're naming from a diagram to figure out the name?
Okay.
Can you go over these one more time, because it's really confusing. Thank you.
Okay, so looking at number 8, and I'll do each of these. All right, let's move some stuff around here. All right, I'll go through each of these one at a time. So looking at this one here, I'll have to redraw it so I can show you some stuff with it. Obviously, you won't have to redraw it because you'll have the thing in front of you. Okay. So for this first one, you have to find the longest contiguous carbon chain. Let me see. I wonder if I can change the colors here. I don't know. I can't remember how to change the colors. Oh, here we go. Ah, ha, 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 ha. There we are. So the longest contiguous carbon chain I'm going to do in red. There we go. I don't think there's any other way to do it. I think that's how it's going to look. All right. Any questions so far?
That makes 9 carbons. Is that true?
1, 2, 3, 4, 5, 6, 7, 8, 9. Yes.
Okay. Okay. Thank you.
Then we circle the substituent groups, and we can name them. Then that's methyl, ethyl, and ethyl. Now remember, you are given this sheet here. See this? That's how you'll know what those are. So the methyl is just a CH3, ethyl is a CH2, CH3, and that's what we have here. So it has to be in alphabetical order. Well, actually, no, let's number this first. Now, when you're numbering it, I think numbering it from this end will give the lowest numbers because everything's closer to the left end than the right. And that would be here, let's see, the ethyls would go first, then the methyl. So it would be 4, 5 diethyl, 3 methyl, 3 methyl nonane.
You name that alphabetically, correct?
Yeah, the E and the M, yeah.
Okay.
So the prefix di for the ethyl does not count in the alphabetization
Nope.
in the name.
Nope, and neither would this stuff here when you've got N or sec or T. Those don't count either. Okay.
The nonane came because we had 9 carbons, right?
In the base, yeah, in
Yeah,
the
'cause
longest chain, that's right.
The base chain goes last after all the
It
functional
always
groups,
does.
right?
Yes, absolutely. Every time.
I have a
Okay.
question about the circles.
Mm.
If there is a branch off the circle that has more carbons than the circle itself, is the circle the parent or is the branch the parent?
Well, if you've chosen the correct chain to start with, that shouldn't happen.
So it'll never be like if you have a hexagon for a circle, it'll never have 8
I see what
carbons
you're
on a
saying.
branch.
Oh, I see what you're saying. No, I try to avoid that.
Okay, but in
Alright.
those situations.
Well, I don't know, Jonathan.
Okay.
I think I'd go with the circle as being the base chain.
Mm-hmm.
Because, well, now, but then you could have cyclohexyl. I suppose, yeah. I suppose as a rule, the one with more carbons, that'll be the parent.
Okay.
But it won't be an issue with any of these because I've made it so that doesn't happen. They're either equal or less. And that's
Like, so when looking at number 8, when the one on the right, I think that's an octagon. I don't know. I can't count. But
yeah,
you can't start off on one of the branch chains and then go to the
we'll do that
center.
one. We'll do that one in a second.
Okay.
All right. So let's look at the one below it here. Okay. Now the longest chain, that one's fairly obvious. And now it doesn't matter if you go up or down here. Either one would have been fine. Okay.
Would you start from the other side?
Well, that's what I was gonna look at. But I thought for this one it wasn't quite as obvious, so I was going to try it from both ends, and we'll see. Okay. So let's look at this. We'll circle the groups here. And I think Jonathan's right. It looks as though there's more groups on the right side rather than the left. So we'd have to number it from this end.
So whichever one has the most groups attached to it is where you start.
Whichever side has more groups closest to it. Remembering that there's 2 groups on carbon 3, so that would count as well. So if I was doing the addition method, just to determine where to start numbering, I do 6 plus 5 plus 3 plus 3 plus 2. And that's because there's 2 things hanging off 3. So that matters as well.
Oh, so it's whichever one has the lowest sum, right?
Yeah, that's right.
Okay.
Now the other one would have been, let's have a look, 5 plus 6 plus 8 plus 8 plus 9. So that would be much bigger.
So many little details.
Oh, I know. I didn't make this stuff up. I'm just letting you know. All right, I'll run the name across the top here. So let's see. We've got the groups here. This one is sec-butyl. And this one here is isopropyl. That's methyl. That's chloro. And that's bromo. Okay, remember that you have the sheet here that will tell you that. So sec-butyl is this one here where the chain comes off that second carbon in the sec-butyl. And then you've got the other ones down here. All right, any questions so far?
Yeah, not really related to this, but are we going to be dealing with any like organometallic compounds, like all these C's and maybe a metallic atom in there somewhere?
No, not generally, not here. That's a bit more advanced. Okay, so alphabetical order. Looks like bromo's first. So it'll be 3
Can I quickly say something about that?
Yeah.
Well, the thing is, though, remember, we're in an organic chemistry. Metals really aren't, like, heavy metals aren't organic.
Oh, but, I mean, we will be dealing with some organometallic compounds at some point. But we won't be dealing with naming them. Like we'll be dealing with Grignard reagents. Those have metals in them, but we won't be talking about naming them because that's what I think the question was specifically about.
Yeah.
Okay.
Okay, so as far as alphabetization, it looks like it's 3 bromo. The next one is the sec-butyl, remembering that the sec doesn't count. What is that? 6 sec-butyl. Oh, that's tricky, isn't it? Oh. Now what's next? Chloro, 3 chloro. After that, isopropyl. I'm running out of room here, so I have to go down here. 5 isopropyl. And then the last one there, methyl, 2-methyl. Decane. Oh, that's a long one, isn't it? All right, any questions?
Wouldn't the propyl come after the methane?
Wouldn't the propyl come after the methane? No, it's isopropyl. Now,
The iso counts.
yeah, because there's no dash. You see that?
Oh.
Oh.
It's its own functional group, not a prefix saying
Right.
how many of something there is, right?
Yeah, that's true. But also, there's no N or anything out the front. Now, an N wouldn't count, and sect doesn't count, and tert doesn't count. Isobutyl, that'd be I as well. But those are one word, so no dashes. All right.
So
Yeah, sorry.
if they have a dash, you go to the second second word, and then you start from there.
That's right.
Okay.
Yeah, it's tricky, isn't it?
Yeah.
Tricky. All right. Okay. Sierra, you asking about this, or somebody was?
It was me with the weird circle hex octagon thingy.
Octagon. Yes, the
Yes.
octagon. All right.
I never much was a geometry person, so this is not my forte.
Okay. Well, with the octagon, all you got to remember is stop. That's the shape of a stop sign. Okay. So we're going to have to number that, and we want the lowest possible numbers. So the way that we would get the lowest possible numbers would be to start here, go here, 1, 2, 3, and then 4. You can take my word for it. There's no other way of numbering that and getting lower numbers, because that'd be 1, 2, 4. If we started here, it'd be 1, 3, 4, and that's going to be more.
So try and get the lowest numbers on the groups.
Substituent groups, yeah.
Constituent groups. Okay. So how do you know where the main chain is? Because what I was wondering was why can't, like, even though that's a, I don't know what that is, CH3 on the end there, like you couldn't take that branch and like make it into a parent thing?
No. I think somebody else was asking something similar to that earlier. And generally speaking, when we have these circles, I try and make it so that everything hanging off is less than or equal to the number in that circle. So there's no way that anything hanging off could be the parent.
Gotcha.
You'd be naming it as a methane in that case. I just don't feel like that would be kosher.
So the chain here is the circle, and we're starting with the side that has the most groups on it, right?
That's right. And we number through the busy area. That's why I started at the 1 and worked my way around. All right, any other questions? All right, so the names of these substituent groups, we've got T-butyl, we've got ethyl, and we've got methyl. Now it has to be in alphabetical order. We start off with the T-butyl, so it'd be 1 T-butyl, because that's going to be based on the B. What's next? Ethyl would be next. 2-ethyl, sorry. And then 4-methyl. And the base chain, cyclobutane.
Now, would we would it be possible to drop one of those O's in the cyclooctane, or is it?
No, because then it's cycloctane. So no, I know it looks kind of weird, but I think it kind of looks cool as well, like 2 eyes looking at you.
So after the methyl group, you don't have to, after like 4-methyl, you don't have to put a dash.
No, you do not want to put a dash. It's Because at,
Okay.
at the end of that, you're done with the substituents. Now you're onto the side chain. There's no dash, there's no space, nothing.
Okay.
All right. All right. Well, I'll do this one because it does show something semi-interesting. Oops. That is awful. That's better. Okay. So the numbering here, remembering that there's two things attached to this one here. So I'd start numbering here. There'd be 1, 2, and then 4. It's effectively 1, 1, 2, 4. And I think that's what a lot of people forget is when you got something attached to one thing, then that counts twice. It effectively counts twice. So that's going to give me the lowest numbering set. So let's see, we've got bromo and fluoro and nitro. Let's see, bromo would be first, 1 bromo. Then it'll be fluoro. And let's see, we've got 1 and 2. 1, 2 difluoro. Now I'm going to mark you off if you spell this wrong. Why am I going to do that? Is it just that I'm being mean?
Because we have a sheet.
Because you have a sheet that actually has the spelling on there. Yeah, that's right. So it leaves you with very little. Let's see, I think it's a decane, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cyclodecane.
For the fluoro, you don't add them together.
Add them together. In what?
The numbers?
No.
No, you leave them separate.
Yeah, because you want to say it's the story you're trying to tell is I need a fluoro on 1 and a fluoro on 2. That's what 1, 2
Okay.
difluoro means.
Okay, that makes sense.
I have a question.
Yeah.
So if you're looking at the name of this molecule and you wanted to draw it, you wanted to know what it looked like, how would you know it's not one big circle and rather the angles are going in like that?
Oh,
Or does it not matter and it's
no,
the
it
same
doesn't
thing?
matter. No, it
Okay.
wouldn't matter. You can draw it as one big circle. I just draw it like this because it looks prettier. Don't you
Okay.
agree? Don't
I do
you
agree.
Yeah, I do too.
So anytime you have something that's like a circular shape, when you name it, it's going to have cyclo and then like decane, octane, or whatever, depending on how many things it has. Okay, and that's on the sheet that we have to remember, correct?
Well, the base change you have to know, yes.
Yeah, it's like there's a paper on like your PowerPoint or something.
There
with
is,
it on
that's
there,
right.
though.
But you know most of them anyway.
Yeah. Wait, 9 is nonane, right?
Yeah.
Okay.
That's a weird one. I know.
It's Italian, like my.
Oh yeah.
Yeah, like I don't know. It kind of reminds me of my grandma. So.
Oh,
yeah.
okay.
Because anyways, I was just wondering.
Fair enough.
Dr. Musgrave?
Yes.
On the previous 2 examples, well, actually the first 2, when there was just a straight chain, you used the other color to kind of show us,
yes.
the longest. We're not supposed to be doing this because it's a circular shape here, or?
Well, with the circles, it's a bit. Well, it's a bit more obvious because you can actually see the circular shape. That
Okay, so it's just the visual.
Yeah, that's right. If you wanted to, nothing to stop you putting it in colors, but it's pretty obvious where it is. So I don't worry about it.
And you didn't go around the whole circle because the branches are attached and stop at that interval?
Yeah. But I mean, I could have, but there's just no point.
Gotcha.
All right, any other questions about that?
So what if that BR there was replaced with an F? How would you name that?
Okay.
I feel like that would be kind of
it would be, okay, so the question is, here's what I'm going to do. I'm going to take this. I'm going to replace that BR with an F. Okay. Okay. Well, I'll just go ahead and do it here. All right. That would be 1, 1, 2 trifluoro.
Oh, okay, got it. That makes sense.
Now notice, this is important. I'm glad you asked me that, Hugo, because see how I've got 1, 1, 2?
Right, yeah.
Not just 1, 2.
Right, that's what I was wondering, because then it could be on either the 1 or the 2, and you'd still have to say trifluoro.
Yeah, that's exactly right. Because you're trying to tell a story here. You're trying to say, well, we've got a fluoro off 1 and another fluoro off 1. And that's the only way to express that. So yeah, you have to put it separately like that. Then 4-nitro cyclodecane, of course, after that.
After people are done asking questions on this one, can we work on drawing a molecule from a name?
We're doing that right now.
Oh, awesome.
Because that was part of the same question, I think. So we'll see. This is a lot easier. So for this one, we've got. So look at you look at it, and say, oh, that's decane. So you do a decane chain. Whoa. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a decane. Then number him. And then put your substituent groups on. So we have 3, 4 dibromo, 3 bromo, and 4 bromo, and then 5, 6 di-T-butyl. Oh, okay, 5 di-T-butyl. There we go. Now, as for figuring out, well, what's T-butyl look like? You go to your sheet here and you figure it out. There he is. But you have to draw it as a line structure.
It's also, you said in one of the previous lectures that it kind of looks like a tree. That's kind of a way to remember it.
Yeah, T. I like that. It looks like a T. All right. The next one, 113 trinitro, 2N propyl cyclohexane. So cyclohexane is a base chain. There he is. Doesn't matter where you number on the circle. Let's see, 113. Got to be a little bit careful, nitro groups. Now I'll show you what you can't do. Well, I don't want to do that. Hang on. I don't like this. Okay. Now, why might I take off for that?
Because the chain is attached to the oxygen, not the nitrogen.
All right, and how would you know it was attached to the nitrogen? Ooh. How would you know it was attached to the nitrogen?
When the C meets with the N there.
Well, because it's here in the diagram. It's here in the sheet you're given. So it does clearly show that the bond is to the N. So you have to be a little bit careful with that. So if you were drawing that, you would have to go. You could do this. You could do N, and you could do O2N like that. That'd be fine. So that's 113 trinitro, and then 2N propyl, and N propyl looks like that. Cyclohexane. So that's it for that one. Yeah.
So the 113 is representing the 3 nitro groups, and you wrote 1 twice because there's 2 on the 1.
Yeah, that's right.
Just like you did with the previous example when you wrote 1 twice for the fluorine. Fluoro.
That's right.
Okay, so when you have 2 groups attached to like a number 1 or 2, you write that number twice.
Well, as many times as it says to. Yes.
Yeah, that's what I mean. Like you write it as many times as you have the numbers.
That's right.
Okay.
I have a question, Professor.
Yeah.
Say there was a double bond in the middle of propyl. How would we indicate that?
Don't worry about it because we're not dealing with any of those kinds of compounds yet.
Okay.
We'll deal with that when we get to test 4.
Oh, okay.
Dr. Musgrave, I have a question.
Yes, Courtney.
In part A, do you see how dibromo doesn't have like a dash between it, but di-T-butyl has one?
It's interesting, isn't it?
Yeah.
Well, now remember that there is a dash here after the T.
Okay.
We need a dash before that as well.
So you would do like, if it was seq-butyl, you would do di-seq-butyl?
Yes, that's right.
Okay.
Pretty nasty, isn't it? But it makes more sense that way. So if there's a dash after it, you'll have to have a dash before it.
Okay.
All right. And C, 1-sec-butyl cyclobutane. All right. Cyclobutane is a 4-carbon chain. Easy enough to number. Okay, 1-sec-butyl. 2-chloro. 2-fluoro. And 3-nitro. There we go. All right, any questions?
Does numbering matter when we're doing this?
No, not the circles. You can number from anywhere.
Okay.
And it doesn't matter which direction either. Clockwise, counterclockwise, as long as you're consistent.
Okay.
D. That's a heptane. Now, often the biggest mistake people make with this is they'll often misread the cycles. They forget the cycle, or they make something a cycle they shouldn't make a cycle. So just be careful with that. So heptane, 1, 2, 3, 4, 5, 6, 7. And we've got 2,2-difluoro. And we've got 4-isopropyl. That's it. All right. Does anybody have any questions?
One more. So the square was the cyclobutane?
That's right.
Okay.
Okay. Any other questions? Okay. Remember, with past tests, I forgot. Well, I didn't forget. I didn't used to give the functional groups, but I do these days. Let me see. I might have one attached to. I'll show you what it looks like. Let's look at the fall 2019. See if it's attached or if it isn't attached. There it is. No, I actually do attach. Oh, no. All right. I guess I did attach the whole thing with the real example and everything. So there you go. All right. So there's your functional group. That's right there as well. Okay. Other questions that people have? Other questions?
Can you just do one more isomer?
One more isomer. Well, I did pull this one up. Let's have a look, see what we have. All right, C2H4OF2. It's not a bad one. Okay. All right. So it's C2H4OF2. 2, the CCO is the only chain that we can really be, it's the only ones we're really worried about. CCO, COC. That's it. Remember, we're only looking at something that has more than 2 or more bonds. So C and O are the only things we can look at initially. And then we can think about where to put the fluorines. So as line structures, they look like this. Actually, let me not put the H on there. Okay. Now we can look at where to put the F on each of these so it becomes different. We can do that.
Well, there should be 2 Fs.
Oh, it's 2 S, is it? Oh, yeah. All right. Oh, that changes everything. All right.
Oops.
Well, not everything, just a little bit. Thank you. There we go. OF2. Thank you. All right. So let's look at combinations then. So we can do an O and an F here. And we can do OF again. We put the F on the end like that. And then I would put 2 Fs off the middle. 2 Fs off the end. And I guess we can do 1 F on each. I think that's it. I don't think there are any more for this one. Can anybody think of another one? Did I miss any?
So can you do 2 fluorines off of the oxygen or no?
No. 'Cause
There's
the
not enough lone pairs?
Yeah, the oxygen only bonds twice.
Gotcha.
So it's got a bond to the C and then a bond to the F. And that's it. That's all you can have. All right. The next one, there's only 2 possibilities I can come up with that. We can put the 2 Fs on the same like that. Or we can put the F on each end like that. That's it. So that one would have 7. Does anybody have any questions? Okay. Other questions?
Could you go over an acidity one?
All right, let's take a look at this one. It's on this test here. Okay. The first thing you want to do is draw out what these look like. Once they lose a hydrogen. Whoops. And it's always the hydrogen lost off the most electronegative element. So it'd be the nitrogen there. So that becomes negative N plus H plus. And the other one be very similar. Okay, any questions so far? Now you'll notice that the negative charge is on the same atom. So the scenario is not one where the negative charge is on different atoms, which means it has to do with the fluorine and the chlorine, which means we have to be talking about delta pluses and delta minuses. Now, I'm going to use an arrow here to make sure I'm very clear about where that delta plus is going. So if delta minus is going on the Cl, the delta minus is going on the F, the delta plus goes on the C that's directly attached to each of those. Now, in the case of the second one, the fluorine, the delta plus is going to be bigger because fluorine is more electronegative than chlorine. So I'm going to go ahead and label these. This will be A, this will be B. I'll call this A minus, I'll call this B minus. So let's see, so I'd say B minus is more stable. Bigger delta plus. F more electronegative. Than N. So sorry, Cl, Cl. And then some statement linking anion stability to acidity. And it would be something like B minus is more stable than A minus. So BH is more acidic than AH. All right. And that would be it. So the delta pluses on the diagram are necessary. If you don't include them, you won't get as many points as you'd want to get. Okay, any questions?
Can you do one with atomic orbital diagrams? There's a question on number 4. It says, draw an atomic orbital diagram and show all the hybrid orbitals. Can you go over that one more time?
Okay. Let's look at
Yeah, I was wondering about that too.
Now, there are videos on all of these. You know, there's going to be one of 8 selected. And there's videos on all of them. So if you watch those videos, then you'll have them all. So we're HCN. Now, if I draw it out, it's going to look like H, C, and then N. And it's going to be a triple bond between the C and the N. The reason I know that is because I know carbon needs 4 bonds and nitrogen needs 3. So it has to be a triple bond. So when I'm doing this, I look at it and I can say, well, that's going to be sp hybridized because it's triple bonded. And the orbital diagram, whoops, the orbital diagram for an sp looks like this, where we've got p orbitals, sp, and sp. Now this would be for carbon. Nitrogen's going to look the same. Notice I draw this parallel as well, because that's how it's set up. It's about orbital overlap. Whoops. He says as he didn't overlap it. There we go. It's not very pretty, I know, but. So that's what we've got for the C and the N there. And the C needs 4 electrons, so I'll go ahead and stick 4 electrons, 1 in each. And you'll notice I put them all up, and on the N, I put them all down. And there's going to be 5 electrons in the N, and the other one goes in here, in the sp. That makes up this lone pair here. So that's going to be the sp hybrid at the end. And then we have to have the hydrogen as well. and that'll stick down. That'll be 1s. And then the P, that's a pi bond there, and the other one's a pi bond as well. And there's a sigma in the middle and a sigma here. That would be it. That would be HCN. As I said, it's one of 8, right? Now the 8 possibilities, you'll find them down here. There we go. See, it'd be one of these 4, one of these 8, sorry. Question 4, one of these 8. I have videos for all of them.
For the CH4 one, do we just simply draw like one, like sp3?
Yeah, it's 4 sp3s. It's sp3 hybridized, yeah. All right. Well, I think we'll leave it there, folks. If anybody wants to hang around and ask me questions, they can, at least for a little while. I do have lab at 2, so I'll see some of you there. And the others of you, I won't see until next Wednesday because Monday's a holiday. Okay. All right. Well, anyway,
So what day is the test?
Wednesday, the following Wednesday. Isn't it?
Yes.
Yeah. Yeah.
So a week from today?
I'm sorry?
Is it a week from today or 2 weeks from today?
No, it's a week from today.
That's what I thought. Okay, thank you.
Yeah. All right. Now, you have to be there, right? I mean, that's the only day, you actually have to be here on test days. But yeah, you'll have to be here.
Quick question. How do you be there? Like, is the Zoom call like normal?
Yeah, it's a Zoom call, but you have to be there on picture. You can't just be there showing your name.
Okay.
And you have to have a mirror. It's all in the syllabus. It's all in the syllabus.
Yeah, just making sure. Okay.
So my printer, when we go to print it, it's in like a separate room in my house. So I have to like, okay.
Just go up, get it, and then come back.
Okay. Did you want me to take my computer with me? Like, so I'm
No,
still on.
no.
Okay.
No, just go get it and then come back.
Okay.
All right. Any other questions?
Do you need us to have like ID on us or?
No, because I've already done that. Remember?
Okay.
First day, right? You were authenticated at that point, Jonathan.
Okay.
All right. Any other questions?
I have one question about resonance.
Well, it's too late to talk about it now in the class, but you can talk to me after the class.
Okay.
So just hang around, Deanna.
Okay.
All right. Any other quick questions?
Where are those videos where you're doing the orbital thing, the resonance structure thing that we just did? I can't remember the name of them.
I'll show you. It's here. It's in the mini lectures folder. Drawing hybrid orbital diagrams and other hybrid orbital diagrams. Those two. Okay.
Thank you.
All right. Okay. Well, that'll be it, folks. See you all later.
Thank you.
Thank you.
Thank you.
Deanna, hang around, please.
Hey, Dr. Musgrave, I have a quick question about lab.
Yes, Morgan.
So obviously, like, I did the procedures and the results and everything, and I watched the video. But I'm like, and I'm sure you're gonna talk about this in lab, but I was like confused on like what to even do for the lab, like.
Well, why don't you? Well, just cool your jets, and I'll explain.
Okay.
At 2 o'clock.
Okay. All
Okay.
right. Thanks.
I'll see you later.
That's great. I have a really quick question about like prefixes for the naming.
Mm.
So, you know how we do like di and tri if there's more than like if there's 2 like fluorine, say, what would you do if you got up to like 4, 5, 6, and 7?
4 is tetra.
Yeah.
5
Would you?
5 is penta.
Yeah, and then hexa, hepta,
Mm.
and so on. Are you likely to give that on the test, like something?
I have given tetra before.
Okay.
Because I've got examples of them, Courtney, in the
Yeah.
worksheets. So
Okay, perfect.
I can justify it. All right, Deanna.
I'm here.
All right, so Deanna, what was your question? It has to be
I
quick
just
though,
want to see an
unfortunately.
example of a resonance question on the test.
Well, I can show you in the keys.
Yeah, that's fine.
All right, so you have the keys here. So let's look at. Well, I won't do that one. I did that one in class. Do this one. So this is what you're asked to do. Is you're given two things, and only one will have. Only one will be capable of resonance. The other one won't be. And then you're expected to show the resonance structures using a resonance diagram, like I'm pointing to here. If you need more details about that, I'd recommend you go back. I don't know if were you here the day we did it, Deanna?
Yeah, I was here.
Okay, but anyway, you can go back and you can watch the Zoom for that.
Okay.
Where I go through exactly how to do it. I'd recommend you do that.
Okie dokie. I will.
Okay. Thanks, Deanna.
Thank you.
Brittany, do you need anything?
Nope, I was just hanging around.
Okay. All right. Well, that's it then, and I will see you all later.